Okay, so the person from the Pre-Business Academy passed out a survey, so y'all can bring that back on Monday. You don't have to fill it out today. Um, uh, but don't forget to bring it back, so put it somewhere. There's an event for pre-business students like yourselves on Wednesday, April 20th, a week from today, right after class, actually. So it'll be the 12 to 2 in the Travis room, which they didn't say where the Travis room is, but that is in the, the new part over the parking lot, the new where a lot of the student offices are now, okay, that's connected to the academic building. Um, that's where the Travis room is. It's in that new building that just opened this semester. And so you will get lunch, and there's a speaker from Drew Hawkins. So he is from this consulting company. So that might be an interesting someone to listen to for pre-business students. So I encourage you to take a chance to, since you get lunch, after class next Wednesday to go listen to Mr. Hawkins. And you can bring that survey back on Monday. Okay, I haven't changed anything much in the order of the homework assignments. So there's another assignment due Monday. That is the chain rule. That's the next one that's coming up. So that's the homework on the chain rule. And then we've got some other assignments coming up. We'll see if we need to adjust the due dates on those. But right now, the first big one that's coming up is that chain rule homework due next Monday. So that's not too many problems. Seems like it was 10 or 11 problems. So you should be able to get through that, although some of them are multi-part problems. But anyway, so that's what we're working on. Let me go back and this. So y'all did better on finishing the marginal analysis homework. So still had some questions about it, though, on how to do certain problems. And one of them that really was challenging, it wasn't really, in one sense, it was not difficult, but you had to read the question carefully, okay? And so that was this actually problem number 2. And so I wanted to look at that one a little bit more closely right now. So it said find the production level at which the marginal cost function starts to increase. Okay. The production level at which the marginal cost function starts to increase. So if you're like me and you're just reading that problem quickly, then you don't notice there necessarily that it says marginal cost function. All right. So not the cost function, okay, but the marginal cost function. All right. And so that can cause some confusion, all right, if you don't read that really super carefully. So I want to look at an example like this one, but we won't do exactly this problem next, okay? And then, but before we get to that one, one that I'm going to do here just literally is this one, okay, number 8. Okay, so just to give you one more example here of maximizing profit. Okay, so I know that one was those last few problems there was causing issues. So he did a lot better at it ultimately. But let's take a look there at this last one just to see one more example of maximizing profit. So if you would, write that down for me, because I'm gonna solve this one, okay? And in the notes here. All right. So again, what you're given here is just a cost formula, okay? A cost function for, in this case, producing some game, all right? So I guess it's a video game, or maybe it's a board game, I don't know, it doesn't say. So we're producing some game there, all right? And here's the cost of producing quantity Q of that game. And then they also give you the demand price equation, right? So again, that's the equation that relates the price that you can charge for an item to the demand for that item. Okay, demand is the amount that you can sell, right? Okay, and as you know, right, there's a relationship between price and demand. Typically, right, if you increase the price, the demand will go down, or if you decrease the price, the demand will go up, right? Okay. And so if you increase the price, the quantity you can sell will go down, or if you decrease the price, the quantity you can sell will go up. Okay, but notice that in this formula, as will often be the case, they've got this relationship between price and demand solved for the variable P. That's the price. Okay, and again, Q is the quantity sold. Okay, so Q is the same quantity that is showing up here as the input variable in the cost formula, right? Okay, and so this is a very basic setup for a question about maximizing profit. Okay, but you do have to do a little bit of work before you can get to that point of solving the problem, because you've actually, in this case, got to write down what is the profit formula, right? So we've done this 2 or 3 times, but there still seems to be some confusion about this. So let's try it once more to see one more example here. Let me scroll down here in the notes. I think I've got some blank pages here, and so I can write so we can see this. Okay. So what was that? What was that cost formula for manufacturing those games? So that was kind of complicated there.
T equals
Not the demand, but the cost. So cost was what? Yeah. 1440
plus 3.1 Q
plus 3.1 Q.
plus 0.0006 Q squared.
Yeah, and you've got to read those that number of decimal places there really carefully, okay? Because that has an impact on this particular problem. All right. So there's the cost formula, and then the price and demand equation was, let's see, this was 8 something, right? 8.6, and then minus, and then they give you this really wonky fraction here, 1 over 440Q, right? Okay. And that gets to be really messy in solving the problem, I think, here ultimately. Okay. All right. So there's the price and demand formula. Okay. All right. So look, to write down the profit function, because that's what you ultimately need here, right? Because that's what you're going to try to maximize is the profit, correct? Remember, profit is always revenue, right? The revenue you can generate from selling the item minus the cost for producing the item, right? Okay, so that's just the basic formulation for computing profit, okay, in just the simplest format possible, right? It's the revenue minus the cost. Well, we have the cost formula, so we can fill in an expression for C of Q here, right? Because they've given us the cost formula, but what they haven't told us is the revenue. So we're going to have to write down that revenue formula, okay? So if you weren't paying careful attention, right, when we were going through this in the notes, that may be where you got stuck here on these last few problems in the marginal analysis homework, okay? But how do you find revenue? It's always the price that you can charge for an item, right, times the quantity of the item that you can sell, right, okay? Okay, I mean that's in its simplest form. That's how you compute revenue, right? It's the price that you sell the item at times the number of items that you sell. Correct? Okay, so the price here in these formulas we're calling P, and the demand, the quantity that we can sell, we're always calling Q, right? So the way you calculate the revenue is just price times demand, P times Q. Okay, but the problem with that revenue formula is you've got two variables there in the formula, so you've got to get rid of one of the variables, and the variable you want to get rid of is P, right? Because we want to express everything in terms of the demand. Okay, so we want the only variable here in our equations, we want it to be Q. All right. So how do we get rid of P here? Well, that's what the demand formula will do for us, right? Because we know the relationship between the price and the demand. The price is going to be 8.6 minus the 1 over 440 times the Q, right? So in this formula, you can substitute for P the 8.6 minus the 1 over 440 times the Q, okay? And see, that gives you a nice formula for the revenue, right, that only has Q in it. It doesn't have P in it, okay? And now you can write down the profit formula that only involves knowing the demand, knowing the value for Q, okay? All right, now let's go ahead and simplify you don't really have to, but let's go ahead and simplify that revenue formula a little bit by multiplying through that Q times the 8.6 minus the 1 over 440. So that gives us 8.6Q minus 1 over 440 times Q squared. Now look, at some point I'm going to have to convert that 1 over 440 into decimals, and that does cause issues in this problem because you really need to write down a lot of decimal places. If you don't write down a lot of decimal places, you'll end up getting almost the right answer but not quite the right answer, and you'll type in something that you think is the right answer into the homework and it'll tell you you're wrong, and you may only be off by a couple of units or something, right? And that really gets frustrating when you're trying to do your homework like that. So let me leave this as 1 over 440 for a second. But ultimately we'll have to convert that to a decimal. I just don't want to do it too quickly. All right, so what's the revenue? It's 8.6Q, right, minus the 1 over 440Q squared, and then minus the cost, which is all of this business. So that's the 1440 plus the 3.1Q plus the 0.0006 Q squared. Make sure you get all those zeros behind the decimal point, because that'll throw you off too. So we have 8.6Q minus 1 over 440 Q squared minus the 1440 minus the 3.1Q, and then minus the 0.0006 Q squared. All right. So it looks like a kind of formidable profit formula, but it's not too bad. It's not really that bad, because these two terms you can combine. 8.6Q minus 3.1Q, that is 5.5Q, I think, right? Okay. And then you have the minus 1440, okay, so you can leave that. And now you've got to take the 1 over 440 Q squared and the minus 0.0006 Q squared, and those two terms you can add together. Now we're going to have to write out some decimal points, some decimal places for the 1 over 440, all right? Give me a lot of them, though, okay? So don't be shy. What is 1 over 440 in decimal terms? That's something like 0.0027. Oh, 227, and then it starts repeating the 27. Is that right? So 27. All right, let's see if we can. Let's write down that many decimal points then, decimal places, see if that's enough. Okay, how many is going to be enough? Look, I don't know. Okay, I can't. It's hard to predict beforehand. All right, how many decimal places is going to be enough? So try to write down a lot. Okay, of decimal places. On a test, I'm not going to make it this complicated, okay? I'm just trying to get you through the homework problem here, all right? And then
So that's Q squared, and then we have minus 0.0006 Q squared. So let's add those Q squared terms together. So that's 5.5 Q minus 1440, and then minus something here. And what is that? What is the sum of those two coefficients? So it's 0.0028 72727 Q squared. Okay.
Yeah, let's see. That 6 was in the fourth decimal place there, so that's going to combine with that. What was it? That 2 here in the fourth decimal place. So you'll end up getting minus 0.00282727. 27, and you can write down a bunch of 27s if you want to, because I think those 27s just keep repeating in the decimal expansion there. Okay. All right. So finally, all right, all we've written down now is the profit formula. Okay. But at least we're one half of the way to solving the problem, right? Okay. Because what we want to do now is find where the profit is maximum. Okay. And that is going to be at a turning point, right? That's going to be at a turning point on the graph of the curve, okay? And how do we look for turning points? That is where the tangent line is horizontal, where the tangent line is flat, and that is going to be where the rate of change is what? 0, right. Yeah, there you got it, right, okay? So sort of a shorthand way of remembering how to solve this problem is, I think the maximum profit is going to be where the marginal profit is 0, where the rate of change of the profit is 0. Okay, so I have to calculate the rate of change of the profit and set that equal to 0. All right, and so I've got to differentiate this formula and then set that to 0, and that's going to be my suspect for where that profit is maximum. Now, I won't be completely certain of that, so it would be good if once I have got my candidate for where the profit is maximum, if I go and look at a graph. All right, that will really help me sort of confirm my answer. But before we make the graph, let's go ahead and see if we can figure out where we think the profit is maximum. Okay, so let's find that rate of change of the profit. And now y'all are so good at doing this, so let me let y'all do that for me, okay? So take a minute or two to do that, and I'm gonna ask someone to share their answer. Okay, I hope they're here today. Okay, looks like most people are here today though. So, all right. So try calculating the marginal profit, the rate of change of the profit. That's a really not a difficult formula to find the rate of change of, right? Okay, if you can. Don't lose track of your decimal places. Okay, that's the hard part. So find the rate of change of that profit. So we've come so far in finding rates of change. You know, in the past we would have had to evaluate a limit, right, to find that rate of change, but now we can do it in just 30 seconds or so. Okay, so that's such a relief. Only have 3 people left. I haven't had a chance to answer a question this semester. So if you're one of those 3, you know your name's coming up, okay? Unless I made a mistake. But we're very loving and supportive in this class, right? Okay, we love each other. All right, so we help you if you have an issue. Okay, so any luck with that? Okay, finding that rate of change. So is Monica? Monica, are you here today, Laura? Oh, Monica, yeah, we missed you last time. All right, so your name came up now. All right, so what is the rate of change, Monica? 5.5, right? Okay, and then minus 0.0. I think there's two zeros there, Monica. Okay, because when you Monica's bringing the 2 down, of course, right? Okay, and multiplying it by the 0.0028. Okay, yeah. So it's 00 what 5, 7, 4, 5, 4, and a bunch of 5 4s after that. Because all these 2 7s are going to turn into 5 4s. Okay, all right. Oh, Q, yeah. All right, thanks. Okay, all right. So we don't want to forget that. Okay. All right. So indeed, that is the marginal profit formula, and then anybody, did we do that right? Did we write that decimal down right?
Yeah.
Okay. All right. So now, all right, now that's sort of step 2. So we're sort of 2/3 of the way through the problem, because now the last thing we want to do is set that to 0, right? Because we want to find where the marginal profit, where the rate of change of the profit is 0, because that's where the tangent line of the graph of the profit is flat, okay? And that means there's a turning point there. Probably there's a turning point there. And that must be where, the profit peaks out, right? Okay? Must be where the profit peaks out is where that turning point is, okay? All right, so all we have to do is set this to 0, yeah? And then solve this equation. That's all we've got to do is set that to 0 and solve that equation for Q. And that should tell us the quantity that we want to produce to maximize the profit. Okay, so solve that equation. Now, that's a very easy equation to solve at this point, okay? So pretty easy. It's just Q to the first power, okay? And then we'll have what we think is the answer to the question there, all right? So solve that for me quickly. So you'll have to do that with your calculator, right? Unless you're a lot faster than I am, you'll have to do that with the calculator. All right, so y'all very quiet. So I think y'all solved that one really fast. All right. So who's next on my list here? Oh, Jeremy. So we missed you last time too, Jeremy. So what's the solution to that equation, Jeremy? The solution to this equation, right? Okay. So just this equation equal to 0. So what's going to be the solution to that equation? So we just want to solve that equation. See, Jeremy, you were doing something else while you should have been solving that equation. Okay. don't think so. That doesn't sound right to me. Okay. So how do I solve that equation, Jeremy? So I've just got this is equal to 0. So what would I do to solve that? So that's easy to solve, right? What? What add what to the other side? Oh, okay. So so let's do that. So I'm going to take this term and add it to both sides, right? So that would give me, I need to have some room to write that down. So I'd have 5.5 is equal to 0.0057454 here, q, right? Okay. And then do what now to finish solving that for q? Divide both sides by what there? Right, yeah, so divide both sides by this big, ugly coefficient, 0.005745454, right? Okay, so, Jeremy, when you do that, what does that work out to be? Approximately. 957 point. All right, so let's round that off just to 957 because this is an item that we're producing, okay, right? And so we're not going to produce a fractional amount of the item, okay? So we can round that off to 957. So that is where the profit is going to be maximum if we produce 957 of these games. Okay, that's where the profit is maximum. All right. Now let's check on that. So let me see here. Let's try making a graph of this, and I'm not sure if I've already. Not sure if I've already made it. I don't think I made a graph of this one earlier. So let's type in that formula for the profit, okay? Because I actually want to look there and see if it looks to me like that profit is maximum there at that 957. Okay, so what was that profit formula again? Y'all help me type it in here. Not the marginal profit, but the original profit formula. So 5.5 Q, right? Okay, and then so 0.00282727, a bunch of 27s there, right? Oh, is there another 2 there? Oh, after the 8. So it's like this? Okay, all right. Is that right? Yeah, q squared, okay. And minus 1440. So there's our profit. And let's see if we can... Oh. So like this? Okay. So there's our profit. Let's zoom out a little bit on that profit. So indeed, there's our profit curve, right? Okay. And see, sure enough, right? At first, when our demand is low, right, our profit is negative, right, because we're not selling enough items there to make a profit. But eventually, right there, a little bit more than, this looks a little bit more than 300, we're going to have a break-even point, right? That's where the profit is going to turn positive, okay? So that's good. And then it looks like the profit continues to increase until we get right over here somewhere, right? Okay? And so that's where the profit is going to max out, right? Okay, and then eventually, if we produce too many of our item, right, the profit is going to start falling again. The reason that the profit starts falling again is when you produce too many of the item is you'll be flooding the market with these items, and to sell the items you're going to have to lower the price, you see, okay? So to sell all those items you would have to lower the price, and that's going to reduce ultimately that's going to reduce your profit, okay? So right there at that peak, right, is where that profit is maximum. And did we hit it right? Looks like it, right? Okay. Yeah, on paper we had 957, right? Okay, and that's what we see on the graph there as well, right? Okay, so that confirms what we got there with pencil and paper, okay, where the maximum profit is. All right, so y'all gonna be able to do this on the test, okay? Because that's gonna be on the test. No, okay. Well, when is the test? That's a good question. It's 3 weeks from last Monday, okay? So I think that's May the 2nd. What? So 2 weeks from next Monday, right? Okay, which I think is May the 2nd. Y'all can check that date to see if that's right. Now, let's back up just slightly. I'm not going to solve this problem, okay? But this is a very similar problem, except writing down the revenue formula here is a little bit easier, okay? So this says a car detailing service estimates that the daily cost for waxing cars there is, what you see, okay? So there's your cost formula. They're giving you that. But notice they don't give you a price-demand formula. They just say the service collects $65 for each car wax, right? Okay? The service collects $65 for each car waxing. So in that problem, well, you know what the cost formula is, right? Okay? So we don't have to rewrite all of that, but you have the cost formula there, right? But what is the revenue formula in that case? Okay? Well, how much are you charging per car? 65, right? And you're going to detail Q of these cars, okay? That's the quantity. Q is the variable that we're representing, that we're always using to represent demand. So price times demand here would be just 65 times Q, you see, okay? In this case, the price doesn't vary with the demand. It's always this fee of 65 for detailing the cars. So that's a little bit easier even in that case to write down what the revenue formula is, okay? And then, as usual, you can write down your profit, right, by just taking the cost and subtracting off taking the revenue and subtracting off the cost, okay? So from this point on, the problem is very much like problem number 8, okay? All right, so now we've seen several examples of the so-called marginal analysis. Let's take another look at marginal analysis, though, but this doesn't involve profit, okay? So that is back to something similar to that problem number 2 on that homework, okay? All right, so this says the cost, this is a different problem, but it's the same thing that you're asked, okay? So the cost to an oil company for producing Q million barrels of crude oil, okay, is given by this cost formula, okay? And so the output now here is, this cost is in millions of dollars, all right? And I'm asking the same question that's asked in that, problem number 2 in that marginal analysis homework. It says, find the production level, so how much oil would you produce so that the marginal cost, not the cost, but the marginal cost, it will start to increase, okay? So notice they're asking you a question here about where marginal cost is increasing or decreasing, right? Okay? Not where the cost is increasing or decreasing, but where the marginal cost is increasing or decreasing, okay? How can we answer that question, all right? So that's what we want to explore here. Okay, where is the marginal cost going to start to increase? Well, I guess we would have to write down the marginal cost, right? Okay. So let's go ahead and calculate the marginal cost. So remember, marginal cost means rate of change of the cost, right? Okay. So let's see if we can calculate that marginal cost. Okay. So y'all try calculating that marginal cost for me. I got one more person I've got to talk to here. Okay. And then we'll be completely through the deck, and then we get to start over again. Yay! Okay. Wonder who I start over again with. Wonder who's the first person I talked to. Okay. I remember that now. All right. Okay. So find for me the marginal cost. So that's just find the rate of change of the cost. That's pretty easy. Okay. Because surely we have to know that, right? To answer this question, where the marginal cost is going to start to increase. Hope I wrote that down right. Okay. All right, so did y'all get that? That's easy now. That's not a hard formula to find the marginal cost for. Okay. That's pretty easy to differentiate that particular function. Okay. All right, so is Jovi here today? Jovi, all right, so what is that marginal cost formula? What now? Okay, well, let's start it then, all right, and then we'll help you finish, all right? So to find that marginal cost, what are you going to do first? Bring down the 3, right, okay? So you'll end up with 3 times 0.24, and then q to what power? When you bring down the 3, remember, what do you do with the 3? You subtract 1, right, okay, so you'll end up here with what? 2, exactly, yeah, okay. And then what about on this one? Bring down the 2, and that's going to multiply by that 5.1, and then we'll get left with q to what power there? 1, exactly. And then what about for this term? Yeah, you'll just bring down the 1, so you'll have 1 times 40.72, right? So I don't need to multiply that 1 in there. That's just 40.72. And then what happens to the q? It's going to be 0, but q to the 0th power is what? Any number to the 0th power is just what? 1, right? So that q is, in effect, just going to disappear, right? Okay? And then what happens to the rate of change of that last term? It's a constant, so it's 0, right, yeah. So that's it. There you got it. So let's... So let's simplify that now, just to
get the coefficients right. So C prime of Q is 3 times 0.24, which is 0.72 Q squared, and then minus, that looks like 10.2 times Q, right? Don't let me make a mistake there. And then plus 40.72, okay? All right, so there's the marginal cost, okay? All right, so got that perfect, all right? Great. Okay, now the question is, where does the marginal cost start to increase, right? Where does the marginal cost start to increase? So to answer this question for the first time, it helps to look at a graph of the marginal cost, because once you see the graph, then the answer there really becomes kind of clear, okay? All right, so what I've graphed here is both the cost. There's the cost formula, okay? There's the cost formula. And notice the cost formula is always increasing, okay? Your cost is always going up. Notice it's not always going up at the same rate, okay? At first your cost is going up pretty quickly, right? And then right around here, notice that the cost is not increasing as rapidly, right? Okay, but the cost is still increasing. And then over here on the right, as we really get to a high production level, then the costs really go up very rapidly. Okay, so remember, this is producing oil, so you can sort of think of why the cost for a graph may look like this. You know, to get started, right, you've got to invest some money, right? So your costs are increasing, and then for a while your costs are pretty stable, right? It doesn't cost you that much more to produce additional oil. But then as you really want to start ramping up your production, it gets harder and harder, right, to extract that oil. So that's when your costs really then start shooting up, okay? So there's the cost. Here is the marginal cost, though, all right? So there's the graph of the marginal cost formula, right? And so notice that at first, what's happening? The marginal cost is going down, right? See, the marginal cost is going down, and then it's bottoming out right about here, and then it starts to do what? Increase, right, yeah. Then the marginal cost starts to increase. So what we're looking for is right around here. That's where the marginal cost starts to increase. And that corresponds to what sort of point? What have we been calling points like this? Where a graph switches from decreasing to increasing, or vice versa? Turning point, right, yeah, okay. So you see where the marginal cost starts to increase, that is at that turning point, right, okay. So what we're looking for here is, where is that turning point? It looks like it's somewhere between 6 and 8, right? But I'm not exactly sure here exactly where it is, right? But it's right at that turning point. That's where the marginal cost, not the cost, but where the marginal cost starts to go up, okay? Where the marginal cost starts to go up. So I'm looking for the turning point for the marginal cost. But how do you find a turning point for a graph? You're looking for where the tangent line is what? Where the tangent line is horizontal, right, okay? And how do you find where the tangent line is horizontal? By taking the what? No, we're looking for the turning point, right? But how do we find the turning point? So how do we find where the tangent line is horizontal? By taking the, begins with an R there. The what? The rate of change, and setting it to what? 0, right, okay? So think about what I just said, because it's a little bit complicated. I've got the marginal cost, okay, and I want to take its rate of change and set it to 0. But keep in mind, the marginal cost is already a rate of change, right? Isn't marginal cost rate of change? So look at what I'm doing here. I'm going to take the rate of change of the rate of change, okay? I'm going to do that twice. I'm going to take, we've already calculated the marginal cost. That's a rate of change. Now we're going to take the rate of change of the rate of change. That is called, that has a name. That's called the second rate of change, okay? Or the second derivative, okay? So we're going to take the derivative of a derivative. Let's see if we can do that, okay? So there's the rate of change formula, and now let's find its rate of change. Okay? By the way, here's how you denote that. Okay? There's your formula for the rate of change, right? Okay? And to find its rate of change, you denote that by just putting another prime there. Okay? You just put a second one there. All right? That means the rate of change of the rate of change. So we're going to do the rate of change twice. Not hard, though, because that's an easy formula to find the rate of change for. Okay? So y'all find that rate of change for me. Okay? That, again, is called the second rate of change or the second derivative. So y'all can do that one super fast if I did the first one right. And now we're back to the top of the deck. Remember, your class participation now is 5% of your grade, right? Okay? So keep that in mind, all right? So I've been very cooperative all semester on participating. That's really great, okay? I'm really pleased by that, okay? Some classes I have to just scream at people, okay, to get them to answer my questions, but y'all haven't been doing that to me, so that's made the class a lot more relaxed, okay? All right, so what is that second rate of change now, okay? And Zaman, you're up. You were the first one before. You remember that? Yeah, okay, all right. Well, now you got an easy one, though, here, too. And probably I won't get back to you, so maybe you won't have to do this again, okay? 1.44Q, right? And then what? Minus 10.2, right? Yeah, so there it is. There's our second rate of change, right? Okay? And we set that to 0. Just set that to 0, and then you solve, and that will tell you where the rate of change starts to increase, right? So this is very easy to solve. We have 1.44Q equals 10.2, because I'm going to add 10.2 to both sides, and then I'll just divide both sides by 1.44. And what does that turn out to be approximately? What now? 7 point what? 7.08. Okay, that's enough. Okay. 7.08 is close enough. All right. Okay. So about at 7.08, that's where the marginal rate of change starts to increase. That what shows on the graph here? Oh, I think so, right? Okay. We knew it was somewhere between 6 and 8. Okay. We knew it was somewhere between 6 and 8, but actually, according to our calculations, that is actually at 7.08. Okay. That's where the marginal rate of change starts to increase. Okay. Now, that's a very interesting point right there. Okay. That's a very interesting point right there, because look at the, let's see if we can find that point. Oh, there it is right there, okay? 7.08, okay? All right, so there's that turning point on the marginal cost, okay? Now look back at the original cost function. Look back at that same number on the original cost function, all right? That is also an important point on the original cost function. This point right here, I don't know if I can pick it out exactly perfectly. This point right there, that's not going to work for me, okay? Oh, well, it came close. Is it? It won't stick, okay? But that point right on the original cost function is also an important point on the, so right there, that point on the, we're at 7.08, that point on the original cost function is also an important point, okay? What sort of point is that? It's not a turning point, okay? It's not a turning point, but that point has a particular name, okay? That is an inflection point, okay? Remember what inflection points were? Inflection points are where the concavity switches, okay? It's where the concavity switches.
Okay? And notice that the cost formula is concave. Which direction is that concave? That's concave down. Right until you hit this point, right until you hit 7.08, and then it becomes concave up. Okay? And then it switches to concave up. And where a curve switches from concave down to concave up, that is an inflection point. Okay? So notice that where you have a turning point on the marginal cost, that corresponded to an inflection point on the cost formula, where it switches from concave down to concave up. That's not just a coincidence, okay? That's not a coincidence, right? That's too strange to be a coincidence. That's going to give us a clue as to how we can find inflection points. Not turning points, but inflection points, okay? While we're at it here, though, let's see if we can ask this, let's see if we can look at the graph and answer this second question. It's easy now, okay? So at what production level is the cost increasing the least rapidly, okay? All right, so remember, cost is always going up, right? Cost is always going up, but my question is, where was it increasing the least rapidly, okay? Where is it going to be increasing the least rapidly? Can you see that from the graph, okay? So there's the cost formula, right? It's always rising, right? Always going up, but it's not always going up at the same rate, right? Sometimes it's the cost is increasing very rapidly, and sometimes it's not increasing very. Sometimes it's increasing more slowly. So I guess my question is, where is the tangent line the flattest? Where is the cost increasing the slowest? Okay. It's at 7.08. That's exactly right. Okay. It's right there at that inflection point, right? Okay. Right there at that inflection point. That is where the cost is increasing. It's almost flat right there, right? Not quite flat, but it's almost flat right at that point. So it's right at that inflection point where the cost is increasing the least rapidly.
Does it matter which line you use to answer that question?
Which line I use?
Do you use the marginal cost one, or do you use the actual cost one?
No, this is, let's go look at the question. Okay, this is where the question can help you, all right? So the question says, at what production level is the cost increasing the least rapidly, right? So you want to look at the cost graph, right? Okay, not the marginal cost graph. But as it turns out, the marginal cost graph really helps you answer that question, okay? Because where that is going up, where that cost is increasing the slowest is right here, where the marginal cost bottoms out, okay? See where the marginal cost bottoms out, that's where that rate is the least, right? Okay? Why is that true? Because what does marginal cost tell you? It tells you the rate of change. So if you want to know where this rate is the smallest, you would look for what's the lowest value on the rate of change, right? Okay? And this is where the rate of change is the lowest. So that's going to be where the marginal cost is going up the slowest. Where the cost is going up the slowest, right? Right there at that value. So it's at 7.083, okay? So at what production level? It's Q equals 7.083, right? Okay? And where does the marginal cost start to increase? Same thing, 7.083. As it turns out, you don't, okay? And so we will talk about that a little bit more, okay? All right? So there we did use the graph, okay? But you really don't have to use the graph to answer that question, okay? As it turns out, all right? Okay. All right, so before we come back to that, though, I want to show you now another rule for, and this is our last one. So I promised you last time this would be the last rule for finding rates of change, okay? So we've learned the chain rule, right? Okay. Spent a couple of lectures talking about that. And here's one more rule, okay? called the product rule. That's also very useful for finding rates of change for formulas that are a little bit more complicated, okay? So if you don't have a function that's just a very simple formula, sometimes you can use the product rule to help you find the rate of change of that formula. Now, the product rule is a little bit lengthier than the chain rule, unfortunately, okay? And it's not applied as often as the chain rule, okay? But it's a pretty easy formula to memorize nonetheless. Once you've practiced it a couple of times, you'll remember it, okay? All right, so here's what the product rule says. It says if you have a function that you can break down as a product of two simpler functions, not a composition, but a product, okay? So the multiplication of two simpler functions, if you can write a formula that way, think of it as the multiplication of two simpler functions, then you can find the rate of change of that function by using the rate of change of the simpler functions. Here's how that works. So you find the rate of change of one and multiply it times the second, and then you take the rate of change of the second one and multiply it by the first. You see how that's working? So if you have this product, to find the rate of change, you take the rate of change of the first just times the second, but not its rate of change, and then the first one times the rate of change of the second one, okay? And it's always addition here, all right? So you just sort of interchange there which one you're going to use the rate of change for, take the product, and add those two terms together. But that's only if you can write the function as a product, okay, of two simpler functions. All right, let's look at an example. All right, so here's a very straightforward example. Suppose you have this formula and you want to find its, suppose you've got this formula and you want to find its rate of change, okay? See, the way we're going to think of that formula as that formula's got a product in it, right? Okay, so we're going to think of that as the product of two simpler functions. The first one will be x, because that's a very simple function, right? And the second one will be e to the x, also a very simple function, see? Okay, so I'm going to think of that formula as the product of two, I'm sorry, let me move this up. I wrote that in the wrong spot. So I'm going to think of that function f of x as the product here of two simpler formulas, okay? One is just x, and the second one is just e to the x. So what the product rule says is, oh, it's really pretty easy to find the rate of change of f, okay? Because here's what you do, all right? First, you would take the rate of change of x and then multiply that times e to the x. What's the rate of change of just plain x, though? 1. So you would just take 1 times e to the x. Okay? Plus, now you go in the opposite order. Keep the x and write down, and then multiply that by the rate of change of e to the x. But what's the rate of change of e to the x? It's e to the x, right? Okay? So that's it. There's the rate of change of that original function f. Okay? Turns out to be e to the x plus x times e to the x. Kind of weird, huh? But that's it. All right? So again, this works whenever you can break down a formula as the product of two simpler formulas. Okay? And that's often the case. All right? Not always, but that's frequently the case. Let's take a look at the next one, because that one's kind of obvious also, right? Okay, here you have this function f of x, and see, f of x involves this big multiplication, right? You have 2x squared minus x times the natural log of x. So clearly, you can think of that as being this very simple formula, 2x squared minus x times this very simple formula, natural log of x, see? Okay. And then to find the rate of change, you can just apply the
product rule.
So what does the product rule say? Again, it says first find the rate of change of your first factor, and then just multiply it times your second factor. So what's the rate of change of 2x squared minus x?
Exactly, 4x minus 1. And then just multiply that times the natural log of x.
Okay, so rate of change of the first one times the second one, plus, all right, now you go in the opposite order.
Keep the first one just as it was originally written, and then multiply by
The rate of change of the second one. But what's the rate of change of natural log of x?
1 over x. Ah, that's it.
So there's your rate of change for the entire function f. Okay, it's this big
Product. You could simplify that in a few ways, but I'm not going to bother to do that. Okay, except I will write this second term as 2x squared minus x over x, because that's what you get when you multiply
2x squared minus x over 1 over x. You get all of this over x. So there's your formula for your rate of change. So it's kind of a complicated formula for the rate of change, but at least we got it written down. Okay, so there it is. No. Okay, so the way it works is rate of change of this one, which is 4x minus 1, right? Times, keep the original second expression, okay? Plus, and now you take the first one just as it originally was and multiply by the rate of change of the second one, okay? So just keep this one and multiply by the rate of change of the natural log of x, okay? So when you write down your answer, you're going to see both of your original factors, okay? You'll see both of your original factors, but then you'll also see their rates of change
in the result, okay?
All right, now this next one is tricky because this one combines both the product rule and the chain rule. So you have to be remember that you've got the chain rule sometimes involved, and also the product rule. All right, first let's break this up as a product. So this is a kind of a complicated formula. Let's break it up as a product. It's obviously a product, right? You have 3x and then times all of that times what's inside the parentheses, right?
So we're thinking of our two factors as 3x and 5 to the 2x plus 4, okay? So there are the two functions that we're multiplying together
to get the formula for f, okay?
So according to the product rule,
I should be able to write down the rate of change of f, okay? But let's take it really carefully here. The first step is really easy because you're going to take the rate of change of 3x and multiply it by the 5 to the 2x plus 4, okay? Well, what's the rate of change of 3x?
there's nothing to that. That's what? 3, right. So you'll get 3 times 5 to the 2x plus 4, right?
So, see, don't get carried away and differentiate the 5 to the 2x plus 4 yet, right? Okay, you just get the rate of change of this one times this one, all right? Plus, now keep the 3x,
and now we have to multiply by the rate of change of
5 to the 2x plus 4.
Oh boy. Okay.
All right. So can I remember now how to find the rate of change of 5 to the 2x plus 4? Well, the rate of change of the 4 is easy because that's what? 0. Okay. All right. So
yeah, it's going to be something like that,
but let's see if we can figure out exactly what it is. So how do you find the rate of change of 5 to the 2x, right? So the plus 4 is easy. That's going to be 0. It's this term is the one that's the hard one, right? So you remember how to find the rate of change of a power like this, especially when the base is not e, okay? So remember what you do? So when you're taking the rate of change of a power, first you always just repeat what? You always just repeat the power. So you're going to end up with 5 to the 2x, right? Okay? But this base is not e, so I have to multiply in something to compensate for that, right? What do you multiply in to compensate for that fact that that base is not e? Yeah, the natural log of what? 5, right. Okay? So you have to multiply in the natural log of 5, okay? But we're not quite through, okay? Darn it, we're almost through, but we're not quite through because this exponent, unfortunately, is not plain x. If that were plain x, I would be finished, but the chain rule says, see, this is where the chain rule comes in. The chain rule says, oh no, I also have to multiply in the rate of change of 2x. What's the rate of change of 2x? 2, right? Okay. So I end up with 5 to the 2x times the natural log of 5 times 2. Okay. Did y'all forget about the chain rule already? Yeah, okay, that's an easy one to forget about, okay? But remember, the chain rule says, okay, if you have in an exponent, if you have a power that's not just plain x, when you take the rate of change of that power, you're going to have to multiply in the rate of change of the exponent, okay? So if you've been doing your chain rule homework, you probably have practiced that, okay? But that's easy to neglect when you're thinking about the product rule. Let's rewrite this a little bit, make this look a little bit cleaner, but I'm not going to rewrite it too much. So this is 3 times 5 to the 2x plus 4. Let me multiply the 2 in here. So I'll have 6 times x times 5 to the 2x. And then I still have, though, that natural log of 5. I guess you can convert that to a decimal if you want to with your calculator. Calculate natural log of 5, and then you can multiply that times the 6. But you'll get an ugly decimal that way.
Would you get that to 6?
I had the 2 right here, and I multiplied it by the 3, yeah, to get the 6x. But I just left the natural log of 5 alone because that's kind of an ugly decimal if you calculate the natural log of 5. So. Like this? Yeah, I'd be really happy to see that. Okay, I'm just trying to, on your homework though, they may want you to simplify. They don't usually want you to simplify a lot, but they may want you to simplify a little bit. Okay, so be thinking about that when you're writing down your answers in your homework. If you think you've done it right and you it keeps marking you wrong, then you may have to do a little bit of simplifying. Okay, let's try another one. This also involves, wow, this one involves the chain rule twice. Okay, but also the product rule. Okay, so the product part of this is obvious because there's clearly two things that we're multiplying together here, right? We have 4x plus 1 squared, right? And then we're multiplying that times the natural log of 4x plus 1. See? So there are the two things we're multiplying together. And so we can apply the product rule to find the rate of change here. Okay, well, let's see if we can do that. So first, we've got to find the rate of change of 4x plus 1 squared. So what do we do to find the rate of change of 4x plus 1 squared? We're going to what? Bring the 2 down. So you'll have 2 times 4x plus 1 to the 1. But this is where the chain rule comes in because I have to multiply in here what? The rate of change of 4x plus 1. What's the rate of change of 4x plus 1? 4. So you've got to multiply in that 4. And then you keep the natural log of the 4x plus 1. That's part 1, right? Plus, now you do it in the opposite order. Okay, so I keep the 4x plus 1 squared. And now I have to figure out what's the rate of change of the natural log of 4x plus 1. Well, that seems like pretty easy because how do you find rate of change of a natural log? What does that always do? Someone said it. What?
Ah, that's right. Yeah, you remember you just invert, right? So you get 1 over 4x plus 1, but now, see, the chain rule is coming into play again, because now you have to multiply in the rate of change of 4x plus 1. What's the rate of change of 4x plus 1? 4. So you have to finish this off by multiplying in a 4. You're going to forget those steps? Probably, right? Okay, no? Okay, right. So we're using both of our high-powered, actually we're using almost every rule we know in this problem for differentiation. We're using the power rule because we brought the 2 down right. We're using the chain rule, right? We're using the product rule. We know how to find the rate of change of natural logs, so we're using that rule. So we really combined a lot of different rules in that one problem. Okay, that's nice, but tricky. So you get this big, ugly formula. Okay, it's got 2 parts to it. Yeah, all of this plus all of this. Okay, so the rate of change there is not a pretty formula, but at least we wrote it down. There it is. Okay, so we got some expression for the rate of change. Oh, let's try. I think I've got one more. Oh, I do. Okay, so y'all can help me. This one is a little bit easier, maybe. All right, so clearly, what are we multiplying together here? We're multiplying together x squared, right, and e to the minus x. So there are the 2 things we're multiplying together. So we'll use the product rule to find the rate of change. So you start with the rate of change of x squared. We can all do that. What's the rate of change of x squared? 2x. So you take that and you multiply it by e to the minus x, right? Plus, now you keep the x squared, and now you've got to find the rate of change of e to the minus x. So how does rate of change of e to the power work? You just get, yeah, e to the power again, okay, Zaman, but you've got one little catch there. That's not just e to the x, that's e to the minus x. So what do I have to multiply in here? Minus 1, the rate of change of the minus x. Yeah, if that were just e to the x, I'd be finished, okay? But since this is e to the minus x, I have to remember to multiply in the rate of change of the minus x. But that's so easy, that's just minus 1. So we end up here with 2x e to the minus x, and then minus, I guess, because that minus 1 is going to change this to negative, x squared e to the minus x. So not a pretty rate of change formula, but there it is. Okay. Sometimes when you find the rate of change, you get an easier formula. Sometimes when you find the rate of change, you get a harder formula. That's just life. Okay. All right. So 3.4 is due on Monday. That is that's just the chain rule, so no product rule in that one. And then 3.5, that homework involves the product rule. I've got a couple more product rule examples for us to do to look at. Okay. All right.